Fouling is the accumulation of unwanted material on solid surfaces to the detriment of function. The fouling materials can consist of either living organisms or a non-living substance. Fouling is usually distinguished from other surface growth phenomena in that it occurs on a surface of a component system or plant performing a defined and useful function, and that the fouling process impedes or interferes with this function. Other terms used in the literature to describe fouling include deposit formation, encrustation, crudding, deposition, scaling, scale formation, slagging, and sludge formation. The last six terms have a more narrow meaning than fouling within the scope of the fouling science and technology, and they also have meanings outside of this scope, therefore, they should be used with caution. Fouling phenomena are common and diverse, ranging from fouling of ship hulls, natural surfaces in the marine environment, fouling of heat transfer components through ingredients contained in the cooling water or gases, and even the development of plaque calculus on teeth, or deposits on solar panels on Mars, among other examples. This article is primarily devoted to the fouling of industrial heat exchangers, although the same theory is generally applicable to other varieties of fouling. In the cooling technology and other technical fields, a distinction is made between macrofouling and microfouling. Of the two, microfouling is the one which is usually more difficult to prevent and therefore more important. Components subject to fouling. Following are examples of components that may be subject to fouling and the corresponding effects of fouling. Heat exchanger surfaces reduces thermal efficiency, decreases heat flux, increases temperature on the hot side, decreases temperature on the cold side, induces under-deposit corrosion, increases use of cooling water, piping, flow channels, reduces flow, increases pressure drop, increases upstream pressure, increases energy expenditure, may cause flow oscillations, slugging in two-phase flow, cavitation, may increase flow velocity elsewhere, may induce vibrations, may cause flow blockage. Ship hulls, creates additional drag, increases fuel usage, reduces maximum speed. Turbines, reduces efficiency, increases probability of failure. Solar panels, decreases the electrical power generated. Reverse osmosis membranes, increases pressure drop, increases energy expenditure, reduces flux, membrane failure. Electrical heating elements, increases temperature of the element, increases corrosion, reduces lifespan. Nuclear fuel in pressurized water reactors, axial offset anomaly, may need to derate the power plant. Injection spray nozzles, incorrect amount injected, malformed jet, component inefficiency, component failure. Venturi tubes, orifice plates, inaccurate or incorrect measurement of flow rate. Pitot tubes in airplanes, inaccurate or incorrect indication of airplane speed. Spark plug electrodes in cars, engine misfiring. Production zone of petroleum reservoirs and oil wells, decreased petroleum production with time. Plugging, in some cases complete stoppage of flow, in a matter of days. Teeth, promotes tooth or gum disease, decreases aesthetics. Living organisms, deposition of excess minerals in tissues is linked to aging, senescence. Macrofouling. Macrofouling is caused by coarse matter of either biological or inorganic origin, for example industrially produced refuse. Such matter enters into the cooling water circuit through the cooling water pumps from sources like the open sea, rivers or lakes. Enclosed circuits, like cooling towers. The ingress of macrofouling into the cooling tower basin is possible through open canals or by the wind. Sometimes parts of the cooling tower internals detach themselves and are carried into the cooling water circuit. Such substances can foul the surfaces of heat exchanges and may cause deterioration of the relevant heat transfer coefficient. They may also create flow blockages, redistribute the flow inside the components, or cause fretting damage. Examples: man-made refuse, detached internal parts of components, tools and other foreign objects accidentally left after maintenance, algae, mussels, leaves, parts of plants up to entire trunks. Quantification of fouling. The most straightforward way to quantify fairly uniform fouling is by stating the average deposit surface loading, i.e., kilogram of deposit per square meter of surface area. The fouling rate will then be expressed in kilogram per square meter s, and it is obtained by dividing the deposit surface loading by the effective operating time. The normalized fouling rate will additionally account for the concentration of the foulant in the process fluid during preceding operations, and is useful for comparison of fouling rates between different systems. It is obtained by dividing the fouling rate by the foulant concentration. The fouling rate constant can be obtained by dividing the normalized fouling rate by the mass density of the process fluid. Deposit thickness and porosity are also often used for description of fouling amount. The relative reduction of diameter of piping or increase of the surface roughness can be of particular interest when the impact of fouling on pressure drop is of interest. In heat transfer equipment, where the primary concern is often the effect of fouling on heat transfer, fouling can be quantified by the increase of the resistance to the flow of heat due to fouling, or by development of heat transfer coefficient with time. If under deposit a crevice corrosion is of primary concern, it is important to note non-uniformity of deposit thickness, localized fouling, packing of confined regions with deposits, creation of occlusions, crevice, deposit tubercles, or sludge piles. Such deposit structures can create an environment for under-deposit corrosion of the substrate material, e.g., intergranular attack, pitting, stress corrosion, cracking, or localized wastage. Porosity and permeability of the deposits will likely influence the probability of under-deposit corrosion. Deposit composition can also be important. Even minor components of the deposits can sometimes cause severe corrosion of the underlying metal. There is no general rule on how much deposit can be tolerated. It depends on the system. In many cases, a deposit even a few micrometers thick can be troublesome. A deposit in a millimeter range thickness will be of concern in almost any application. Progress of fouling with time. Deposit on a surface does not always develop steadily with time. The following fouling scenarios can be distinguished, depending on the nature of the system and the local thermohydraulic conditions at the surface. Induction period. Sometimes, in-and-ill fouling rate is observed when the surface is new or very clean. This is often observed in biofouling and precipitation fouling. After the induction period, the fouling rate increases. Negative fouling. This can occur when fouling rate is quantified by monitoring heat transfer. Relatively small amounts of deposit can improve heat transfer relative to clean surface, and give an appearance of negative fouling rate and negative total fouling amount. Negative fouling is often observed under nucleate boiling heat transfer conditions of forced convection. After the initial period of surface roughness control, the fouling rate usually becomes strongly positive. Linear fouling. The fouling rate can be steady with time. This is a common case. Falling fouling. Under this scenario, the fouling rate decreases with time, but never drops to zero. The deposit thickness does not achieve a constant value. The progress of fouling can be often described by two numbers: the initial fouling rate and the fouling rate after a long period of time. Asymptotic fouling. Here, the fouling rate decreases with time, until it finally reaches zero. At this point, the deposit thickness remains constant with time. This is often the case for relatively soft to poorly adherent deposits in areas of fast flow. The asymptote is usually interpreted as the deposit loading at which the deposition rate equals the deposit removal rate. Accelerating fouling. Under this scenario, the fouling rate increases with time. The rate of deposit buildup accelerates with time. Mechanistically, this scenario can develop when fouling increases the surface roughness, or when the deposit surface exhibits higher chemical propensity to fouling than the pure underlying metal. Seesaw fouling. Here, fouling loading generally increases with time, but, when looked at in more detail, the fouling progress is periodically interrupted and takes the form of sawtooth curve. The periodic sharp variations in the apparent fouling amount often correspond to the moments of system shutdowns, startups or other transients in operation. The periodic variations are often interpreted as periodic removal of some of the deposit. Steam blanketing has been postulated to occur between the partially spooled deposits and the heat transfer surface. However, other reasons are possible, e.g., trapping of air inside the surface deposits during shutdowns or inaccuracy of temperature measurements during transients. Economic and environmental importance of fouling. Fouling is ubiquitous and generates tremendous operational losses, not unlike corrosion. For example, one estimate puts the losses due to fouling of heat exchangers in industrialized nations to be about 0.25% of the GDP. Another analysis estimated the economical loss due to boiler and turbine fouling in China utilities at $4.68 billion, which is about 0.169% the country GDP. The losses initially result from impaired heat transfer, corrosion damage, increased pressure drop, flow blockages, flow redistribution inside components, flow instabilities, induced vibrations, fretting, premature failure of electrical heating elements, and a large number of other often unanticipated problems. In addition, the ecological costs should be considered. The ecological costs arise from the use of biocides for the avoidance of biofouling, from the increased fuel input to compensate for the reduced output caused by fouling, and an increased use of cooling water in ones through cooling systems. For example, normal fouling at a conventionally fired 500 MW power station unit accounts for output losses of the steam turbine of 5 MW and more. In a 1,300 MW nuclear power station, typical losses could be 20 MW an hour. In seawater desalination plants, fouling may reduce the gained output ratio by 2-digit percentages. The extra electrical consumption in compressor-operated coolers is also easily in the 2-digit area, in addition to the operational costs. Also, the capital cost increases because the heat exchangers have to be designed in larger sizes to compensate for the heat transfer loss due to fouling. To the output losses listed above, one needs to add the cost of downtime required to inspect, clean, and repair the components, and the cost of actually doing this maintenance. Finally, fouling is often a root cause of serious degradation problems that may limit the life of components or entire plants. Fouling control. The most fundamental and usually preferred method of controlling fouling is to prevent the ingress of the fouling species into the cooling water circuit. In steam power stations and other major industrial installations of water technology, macrofouling is avoided by way of pre-filtration and cooling water debris filters. Some plants employ foreign object exclusion program. Acoustic monitoring is sometimes employed to monitor for fretting by detached parts. In the case of microfouling, water purification is achieved with extensive methods of water treatment, microfiltration, membrane technology or ion exchange resins. The generation of the corrosion products in the water piping systems is often minimized by controlling the pH of the process fluid, control of oxygen dissolved in water, or addition of corrosion inhibitors. For water systems at relatively low temperatures, the applied biocides may be classified as follows: inorganic chlorine and bromide compounds, chlorine and bromide cleavers, ozone and oxygen cleavers, unoxidizable biocides. One of the most important unoxidizable biocides is a mixture of chloromethylisethiozolinone and methylisethiozolinone. Also applied are dibromnitrilopropionamide and quaternary ammonium compounds. For underwater ship hulls, bottom paints are applied. Chemical fouling inhibitors can reduce fouling in many systems, mainly by interfering with the crystallization, attachment, or consolidation steps of the fouling process. Examples for water systems are chelating agents, long-chain aliphatic amines or polyamines, organic phosphonic acids, or polyelectrolytes. For fired boilers, aluminum or magnesium additives can lower the melting point of ash and promote creation of deposits which are easier to remove. See also process chemicals. Magnetic water treatment has been a subject of controversy as to its effectiveness for fouling control since the 1950s. The prevailing opinion is that it simply does not work. Nevertheless, some studies suggest that it may be effective under some conditions to reduce buildup of calcium carbonate deposits. On the component design level, fouling can often be minimized by maintaining a relatively high and uniform fluid velocity throughout the component. Stagnant regions need to be eliminated. Components are normally over-designed to accommodate the fouling anticipated between cleanings. However, a significant over-design can be a design error because it may lead to increased fouling due to reduced velocities. Periodic online pressure pulses or backflow can be effective if the capability is carefully incorporated at the design time. Blowdown capability is always incorporated into steam generators or evaporators to control the accumulation of non-volatile impurities that cause or aggravate fouling. Low fouling surfaces are an option for some applications. Modern components are typically required to be designed for ease of inspection of internals and periodic cleaning. Online fouling monitoring systems are designed for some applications so that blowing or cleaning can be applied before unpredictable shutdown is necessary or damage occurs. Chemical or mechanical cleaning processes for the removal of deposits and scales are recommended when fouling reaches the point of impacting the system performance or an onset of significant fouling-induced degradation. These processes comprise pickling with acids and complexing agents, cleaning with high-velocity water jets, recirculating with metal, sponge or other balls, or propelling offline mechanical, bullet-type tube cleaners. Whereas chemical cleaning causes environmental problems through the handling, application, storage and disposal of chemicals, the mechanical cleaning by means of circulating cleaning balls or offline, bullet-type cleaning can be an environmentally friendlier alternative. In some heat transfer applications, mechanical mitigation with dynamic scraped surface heat exchangers is an option. Also, ultrasonic or abrasive cleaning methods are available for many specific applications.